Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. This is module 19 and in this module we are going to consider a different type of incidence which is called as oblique incidence. Okay. This case is important because in many scenarios, especially when we talk of waves in guided media, we can think of the waves or the modes propagating in that guided media as being composed of successively reflected obliquely incident waves. Okay. So, whatever we are going to learn here, we can apply it to the study of waves in the guided media, which we are going to do in the next, not next, but some other modules after we finish this properties of plane waves, right. So, with that let us actually look at what the physical situation is. The physical situation for the problem is kind of the same. So, you have this plane of interface wherein you have a medium 1 and a medium 2. Previously we considered angle of incidence in such a way that the propagation vector was coinciding with the normal to the interface plane. So, the normal to the interface plane was the z axis and then the angle of incidence was coinciding, the propagation vector of incident, reflected and transmitted media were coinciding with exactly the same z direction, the normal to the interface. Okay. Now, instead of this propagation vector coinciding, what happens when the propagation vector is at an angle theta, we will call as theta 1 because we want to distinguish two angles. What happens when the incident wave arrives at this plane of interface with an angle theta 1 as measured from the normal. So, this is the normal, move theta 1 here and this is the angle of incidence now. So, what happens? We know from Snell's law two things are going to happen. One is that there will be a transmission into the second media whose angle of refraction theta 2 can be related to theta 1 by the following Snell's law. So, you have n1 sin theta 1 equals n2 sin theta 2, where n1 and n2 are the refractive index of the media, indices of medium 1 and medium 2. Okay. So, this is a law which allows you to determine what is theta 2 given n2, theta 1 and n1. There is another law which states that angle of reflection, which we will call as theta reflection, would be exactly equal to the angle of incidence, right. So, what it means is that if I consider again this obliquely incident wave, this wave as it approaches, okay, part of that one will be reflected onto this side, right. So, part of the wave is actually reflected onto this side and some portion of the wave is transmitted to the second medium with an angle that is different from the angle of incidence. Now, nowhere with this Snell's law you actually are specifying or you are actually able to determine how much of the power that has been incident is actually being reflected and how much of the power is being transmitted, right. So, to obtain that important information, we have to go back to the electromagnetic perspective of this problem. Moreover, it is not just the amplitudes that are, or rather the power relationships that are important, but also something interesting happens with the amplitudes as well. Okay. Moreover, this Snell's law, the so called Snell's law actually fails for certain scenarios which will be very important when you consider what is called as optical waveguides. Okay. So, for all these reasons we need to go back to the electromagnetic perspective, okay, starting with electromagnetic waves and then apply boundary conditions to really understand how much power is being reflected and what exactly happens if the medium of if the first medium has a refractive index or equivalently the permittivity greater than the medium second medium's refractive index. So, all those things can be answered by looking at Maxwell's equations or wave behavior at the boundaries. Now, before we go further, we actually have to have two kinds of waves that we can think of. Okay. So, let us return back to our picture. This is my interface plane and I have this angle of incidence, I have this incident, this one. This is the propagation vector, the black one is the propagation vector. Please imagine that this is at an angle. Okay. Now, I can have two cases. I can have electric field in this plane, okay, which would be, if you look at it in this manner. So, it should be perpendicular. So, it should be like this, let us say. So, this electric field lies in the same plane of interface, okay. Or I can have the other way around, I can actually have the magnetic field in that plane, okay, maybe in that slightly different this one, we define the incident plane as the one that would be concerned with this particular plane, right, the one that would involve the normal and one of the tangential components. So, if we take the tangential component to be along the x, then any the electric field can lie along in the xz plane, okay, or the magnetic field line can lie in the xz plane. Okay. Depending on these two choices, you have what is called as transverse electric polarized waves. Okay. In this case, you have the magnetic field in the same plane as the interface plane, which we have, I mean, as the plane of incidence, which is x and z. Okay. Or you can have transverse magnetic wave, which is written as Tm when it is the electric field which lies in the plane of incidence, which we take as x and z. So, as you have seen here in this diagram, I am assuming that the electric field lies in this plane of incidence, and therefore, I am describing what is called as transverse magnetic, because the magnetic field will be perpendicular to these two lines, right. So, the magnetic field will be perpendicular, and that is why it is the transverse magnetic waves that we are considering. Okay. So, the rest of the ideas are quite simple. All you have to do is to find out appropriately the boundary conditions. There are 4 boundary conditions. ET1 will be equal to ET2, no doubt. HT1 will be equal to HT2, no currents. This medium has refractive index or equivalently the permittivity epsilon R1. This medium has a permittivity epsilon R2, and this time I have switched x and z axis. I have taken the z axis downwards and x axis along the horizontal thing, and the waves are given by these green lines, and the electric field components are shown. By the way, I have taken the electric field component for E2 to be completely arbitrary. Equations will tell us whether the direction is this one or the direction of electric field E2 should be reversed. Okay. So, do not worry about that. This is the incident wave, this is the reflected wave, and this is the transmitted wave. Okay. So, you have these 3 waves and you have these 2 boundary conditions. You can also have, of course, the other boundary conditions, which is Bn1 equals Bn2, and finally epsilon 0 En1, or rather epsilon R1 En1 to be equal to epsilon R2 En2 coming from the D field normal relationship. So, these are the 4 boundary conditions that you have, and you have to use these boundary conditions to tell us or to find out what would happen to the reflected power and transmitted power. Okay. So, let us go with this. So, I have this k vector here, which is k1, this k vector is also k1, whereas this k vector is k3. K2 is equal to k1 because, or rather I will write it as k2 equals k1 because these two actually in magnitude they are in the same medium, right. Okay. And this is k3. Okay. We will now look at the tangential component for the electric fields in medium 1 and tangential component of the electric field in medium 2 and equate the two, right. So, I have blown up this portion of the picture here, okay, because I want to talk about the electric field angles. So, you can see that if this is the x axis, this is the z axis, this is the plane of interface, okay, I have this electric field E1 itself having 2 components, which is ET1 and EN1. Okay. The tangential component of course is given by E1 cos theta 1, that is the amplitude, but there is also a phase. Now, what is the phase here? In so far what we have considered, our direction of k was exactly equal to, it was actually equal to one of the normals or one of the unit vectors. It could be z, x or y, we have taken it to be z. So, our k vector could be written as whatever the magnitude of the k vector, say in medium 1 times z, right. So, I could have written this k1 in a vector form as k1, which is the magnitude, times the angle, which is z. In this case that is not true. In this case I have the k vector itself at an angle. Okay. So, the k vector should actually be written as kt1 along say x plus kn1 along z, right, because you can take this line and then decompose this into 2 lines of this particular nature. One will be along x, one will be along z. And what is the value of kt1? kt1 will be, so this k vector can be written in terms of the, so along z it would be k1 cos theta 1 z plus k1 sin theta 1 x. So, this would be the k vector, k1 vector. Okay. What about this e power minus j k1z that we were writing earlier? We were writing earlier as very simple as k1z, because you could take this k1 vector and the position vector r. In the previous case the position vector r was simply z hat, because z was the only direction in which the wave was propagating. So, when you take the dot product of k1 and r, this phase factor was simply equal to e power minus j k1z. But in this case the position vector can be in the x and z plane. So, at any point that you can consider, okay, which would be described by x and z. So, that point can be described by both x and z values. The phase factor that should be written will be e power minus j k1 dot r, where r is given by x hat plus z hat, okay, meaning that if you now combine everything. So, what we have here is the position vector r given by x hat plus z hat. Now, I will erase here itself so that this can be written correctly. The phase factor corresponding to the incident wave, okay, would actually be given by e power minus j k1 sin theta 1 x plus k1 cos theta 1 z. Okay. So, this would be the phase factor that should be appended to the amplitude. So, this e power minus j k1 sin theta 1 x plus k1 cos theta 1 z should be accompanying the tangential component that we have for electric field E1. Okay. See, the electric field E1 would have the tangential component which is given by this ET1. So, this is ET1, which is of course making an angle of theta 1 with respect to the electric field in the medium 1, sorry, with respect to this axis. So, you write down this in terms of tangential as well as the normal component. Normal you are not worried at this point, tangential component has an angle of theta 1 with respect to this axis. So, you simply have E1 cos theta 1, E1 being the magnitude of the incident electric field, cos theta 1 giving you this one. Okay. Now, K3, which is in the same direction as K1, will also be given by the same expression, except replacing theta 1 by theta 3. Okay. So, the tangential component in second medium, okay, the tangential component of the electric field in the second medium of course has the same angle also. So, if you look at this electric field, you see that this electric field will be in the same angle, everything is same, so except theta 1 will become theta 3. So, I can write down ET3 as E3 cos theta 1 e power minus j K3 sin theta 3x plus K3 cos theta 3z. Okay. So, that is for the transmitted electric field. How about the electric field E2? Now, E2 is slightly different, because K2 vector itself will be given by K2 magnitude, which of course actually is equal to K1, because magnitude wise they should be the same, they are in the same medium, right. So, you will have K1 itself. Now, look at this, the direction along z will be opposite to the incident wave, that is how of course the wave is propagating along minus z direction. Therefore, you can write this as K1 sin theta 1 x, why theta 1, because theta, or rather we will write it as K2x at this point. Okay. So, K1 sin theta 2x, sorry, this would be x hat, that is the vector along the x direction, plus or rather minus, because now K2 vector is minus K1 cos. So, I have this K2 cos here, sorry, along x, hold on, I made a small mistake here, it should have been K1 cos everywhere, we put in sin instead of cos. So, this actually should be cos, right. Let me write down this correctly. So, this is your K1 at an angle theta 1. So, along the x axis will be K1 cos theta 1, K1 sin theta 1. Okay, this is fine. I mean, whatever we wrote earlier was actually fine. So, we will go back and write it, K1 cos theta 1 along z, K3 sin theta 3 along x, and K3 cos theta 3 along z. So, this is all right. I mean, I thought cos and sin should be inverted, but no, it is actually correct. So, K1 cos theta 1 will be along z, K1 sin theta 1 will be along x, but for the reflected wave which is making an angle theta 2 here, you have K1 or minus k1 cos theta 2 because this is along the minus z direction, right. So, this would be along the minus z direction, and along x direction it would be positive, I mean it would be along the same plus x direction as k1. Okay. So, the reflected wave vector k2 can be written as k1 sin theta 2 x minus k1 cos theta 2 times z. Okay. So, I can write down ET2, which is the tangential electric field. What is the amplitude of the tangential electric field? Well, you have to again rewrite this picture and then determine what is the corresponding amplitude there. So, let us put down the amplitude here. The picture that I am now looking at is when electric field is making this angle E2, this angle is theta 2. So, clearly onto this one, this line makes an angle of theta 2. Between this line, that is electric field E2, and this normal will be 90 minus theta 2, correct, because this E2 is perpendicular to K2. So, this angle will be 90 minus theta 2. However, these two lines, which is the perpendicular line and the horizontal line, they themselves are 90 degrees apart. Therefore, this angle is basically theta 2. Okay. So, you can write this as E2 cos theta 2 along x direction, that would be along the minus x direction, and E2 sin theta 2, that would be along the z direction, and it would be along minus z direction. However, we are interested in the tangential component, therefore, I can write this as E2 cos theta 2, but this is along the minus x direction because of the way that we have taken the electric field to be. So, this would be minus E2 cos theta 2 multiplied by this K2 phase factor, right, multiplied by this phase factor, which is given by minus j K2, and K2 cos will be along z, K2 sin will be along x. So, we have already written that one. So, minus K2 sin theta 2 x minus K2 sin, or rather cos theta 2 times z. So, we have the three individual components. It took us a little bit of effort to find out the correct amplitudes and other things, that is because we are dealing now with oblique incidences. Normal incidence would be very simple. You also have seen that there is a small change in our electric field coordinates, because for the normal incidence theta 1 will be equal to 0, okay, which assume that theta 3 is also 0 and theta 2 is also 0. Why? We will see it shortly, but if you assume all these thetas to be 0, then you will clearly see that all the x dependent phase factors will go away, as it should, because there was no e power minus j k something times x in the normal incidence case. All the waves were propagating either along plus z direction or along minus z direction. All cos theta factors will become 1, Et1 will be along the plus x direction, Et3 will be also along the plus x direction. Okay. However, Et2 has now become along the minus x direction. Okay. If you did not want this minus x direction, all you could do is to simply switch this direction of the electric field. So, instead of considering the electric field in this manner, you consider the electric field to be in the same direction as E1, and then adjust this minus sign in the H case. Okay. So, when you do that, you can remove the minus sign and make this one plus without changing any of the other arguments. Okay. This is just kind of consistency between this module and the previous module. If you wish that, you could do this. Okay. If not, you can continue with the original assigned directions and work throughout. The equations will anyway tell you that you will have a minus sign or a plus sign. Okay. Now, all I am doing here is to try and make everything to be consistent with the previous module. Therefore, even though I started off with an electric field in the direction that I showed in the green line, I am now switched it over to the orange line simply because I want to be consistent with the previous one. However, our original expressions that we started out in this module are also valid. I would encourage you to take this as an exercise and continue that next part of the development with the original diagram as well. Okay. For now, I am simply assuming that electric field is going to be in this direction, just to be consistent with the fact that when theta 1, theta 3 and theta 2 are all 0, we will end up back into the normal incidence case. Okay. Anyway, so this is K2, we have written everything we have now written. So, we have a set of equations which are valid for electric field. Okay. Now, what should we do? Well, we know that Et1 plus Et2 should be equal to Et3, that is total tangential electric field medium 1 should be equal to medium 3, right. And where should this equality be present? This equality should be present at z equal to 0 plane, but unlike the previous case, because the phase factors will be dependent on x now, this should be valid for all x. Okay. This expressions that the tangential electric field should be valid for all x. What it means is that if I consider the electric field to be landing at this point and then calculate the tangential electric field, it does not matter where the tangential electric field lies on the x axis, right. At every point on the x, or rather every point on the x should satisfy this equation. Okay. So, that is the critical part of it, and now when you impose the condition that at z equal to 0 and for all x, the sum Et1 plus Et2 should be equal to Et3, you can write this as, okay, with z equal to 0, all these terms will go to 0, we do not have to worry about it. So, the expression will actually become E1 cos theta 1 e power minus j k1 sin theta 1 x plus E2 cos theta 2. Okay. Please note that I have switched the convention here, it does not matter, and then I have e power minus j k2 sin theta 2 x, that should be equal to E3 cos theta 3 e power minus j k3 sin theta 3 times x. Okay. And because these equations have to be valid for all x, the only way this can happen is that these individual phase factors are all equal to each other. Okay. So, these individual phase factors being equal to each other means that I have k1 sin theta 1 x should be equal to k2 sin theta 2 x, which should be equal to k3 sin theta 3 times x. Now, obviously in this expressions k2 is given by omega square root mu naught epsilon r1, which is actually equal to k1 magnitude. Why? Because both incident and reflected waves are in medium 1 and medium 1 is characterized by permittivity epsilon r1. Okay. And that immediately implies that sin theta 1 must be equal to sin theta 2. And what is the limits on theta 1 that we can have? Well, this theta 1 can be 0, which corresponds to normal incidence, and all the way to theta 1 equals pi by 2, in which case the wave will be riding along the plane of interface, it will be riding along the plane of interface with the electric field appropriately directed. Okay. So, this kind of a wave, right, where the electric field is along the ground kind of a thing and this is riding along the parallel interface plane, is called as grazing angle incidence. Okay. Whereas this way was called as normal incidence, this is oblique incidence, this is called as grazing incidence. The wave is kind of gliding or grazing the surface and electric field line actually lies in that particular plane. Okay. Electric field is parallel to this ground. Okay. The other way would of course be that electric field is perpendicular, the magnetic field would be gliding along this surface, right. So, that would correspond to transverse electric or vertical polarization, this would correspond to parallel polarization. Okay. So, with that in mind, if you look at the equations, theta 1 can go from 0 to 90 degrees. So, if you sketch sin theta 1, it would look something like this up to 90 degrees. So, this is 90 degree done. So, if you have two sine functions equal to each other over 0 to 90 degree interval, the only way that can happen is when theta 2 is equal to theta 1. Okay. This is in fact so called Snell's law of reflection. In fact, what we have seen is there is nothing like a law, it is a simple consequence of boundary conditions, right. So, all these laws that we have learned so far are nothing but consequences of boundary conditions. Okay. So, that is the boundary condition. The second equation that you have, k1 sin theta 1 is equal to k3 sin theta 3, right, is also Snell's law, but this equation tells you that for the same frequency omega, this would be square root epsilon r1 sin theta 1 equals square root epsilon r2 sin theta 3. Okay. But because epsilon r1 epsilon r2 square roots are nothing but refractive index, this is n1 sin theta 1 equals n2 sin theta 3. Okay. So, this is another of Snell's law, this is called as Snell's law of refraction. Okay. So, we have recovered this Snell's law as a consequence of boundary conditions, but we are not done yet, right. What we have done so far is to simply equate the tangential electric field and get an equation in this particular manner. So, we will write the equation for our use now. So, we have E1 cos theta 1 plus E2 cos theta 2, where theta 2 and theta 1 are actually equal to each other, is actually given by E3 cos theta 3, right. So, this is one equation that you need to keep in mind. Now, we need to supplement this equation with the magnetic field equation. How would the magnetic field equation be? Well, you go back to this picture here, you assume that this is H1 magnetic field and this would be say H2 magnetic field, and then you will have H3 magnetic field. In all these cases the magnetic fields are in the perpendicular direction, except that for the reflected field we will make the magnetic field go in the opposite direction, so that E cross H would be propagating along minus Z direction. E cross H, if you take H to be upwards in this manner, E cross H would be propagating in this direction. E cross H in the second medium would also be propagating in the given K3 direction. If you reverse the direction of H2 to downwards, E cross H would actually propagate in the K2 direction. Okay. So, with that I can write down the expression for H as, since H is transverse or rather tangential everywhere, it is actually along the plane of interface, I will have H1 minus H2 is equal to H3. Okay. So, I will have this particular equation, but H1 is basically E1 by eta 1, this would be E2 by eta 2, this would be E3 by eta 3, and I need to group the terms together, solve again for E3 by E1, which we will call as the reflection coefficient, okay. And then you will have E3 by E1 is called as the transmission coefficient, because this tells you the ratio of the electric field that has been transmitted to the electric field that has been incident. E2 by E1 we will call as the reflection coefficient, and we will get the expressions for these two. Okay. Since I am running out of time, I will stop here and we will start from these expressions, derive the transmission and electric transmission coefficient and reflection coefficient, and also tell you about that peculiar scenario where this Snell's law actually fails. Okay. Thank you very much.